Hi friends, welcome back. Today we are back with one more very interesting tutorial. What we are going to do today is we are going to see how we can do a distributed model training in a Google Cloud virtual machine. I have one GPU, a Google Cloud virtual machine VM with one GPU because there is a quota for everybody. I have requested for quota. Once I get a quota, I will update the video with multiple GPUs. But as of now, we will see how we can run distributed training on a Google VM with a GPU. So just to brush on some of the basics, basically we'll take reference of this particular site where the distributed training comes in two different scenarios: model splitting across GPUs and batch splitting. For today's tutorial, we will look at how batch splitting across GPUs is done. Batch splitting means basically you are splitting the data that you are using to train the model across multiple GPUs or across multiple nodes or within the same node, uh, two different GPUs in different ways. So there are three basic types. One is accumulating gradients, where you are using uh, for example, if the batch size supported by the GPU is only 32, but the actual batch size you want to use to tune the model is 256. So what you would do is you would divide 256 by 32 into 8 equal parts, and you would calculate the gradients uh, uh, for each of those steps, and then we accumulate them for all the 256 steps, and we perform optimization at the end. This particular thing is called accumulating gradients. So, but there is a disadvantage for it, because it will take a lot of time, because this is not being trained in a parallel fashion. We have to accumulate all the gradients and then optimize it. We have to wait for all of the batches to complete. So the next type of thing is called NN dot data parallel. Basically, what you are doing is there is a single process, but you will for both the GPUs, but you will spawn a different thread and you will have a main process, and all for the forward pass the model is replicated on each device, and the gradients of each replica uh, are gathered and they are applied on the master GPU to update the model weights. And again, this is in the next pass or in the next iteration, this particular updated model is carried forward in the forward pass to across all the GPU devices. There is parallelization in this particular method, um, but the disadvantage is that there is a single process. There are no two different processes. It's a single process, and this particular process spawns a different thread on the GPUs. This has certain interpreter lock issues. It is not fully parallelized distributed training setup. So the third type is called distributed data parallel. The one which we saw just now is NN dot data parallel. The third one is called distributed data parallel, where we'll have two different processes. One will be a master node, and the other one will get back to the master node. And there are different backends, like NCCL is GPU, GLO is CPU. Oh, so it distributes um, the batch across multiple GPUs, and there are separate processes that are spanned, and there is a full parallelism across these GPUs. So this is, we use Torch API's distributed data parallel interface to implement this.
And as you can see here, they're mentioning like number of processes, and if there is one node, we'll mention one node, and if there are two GPUs, this will be two here. And node rank 0 means it's the master node and master address, master IP address, and the port where it is open for traffic, and this is the Python script where the training runs. And this is the secondary node, which again has the IP address of the master node and the master node's open port, and the uh, Python script where the training is done. Uh, so basically this is what it is. But again, this is advantage. This has better in terms of like parallelism, but there is also one issue with batch normalization, because we need to implement a different type of batch. Python provides a sync batch norm as a replacement wrapper, which calculates the batch statistics across the whole batch, across the GPUs, and then it syncs it up. So this is the overview. For today's thing, we will do it on a single GPU. So basically it is distributed data parallel, but it will be implemented on a single node on a single GPU. When I have access to two different nodes with one GPU each, I will try to implement it on those two and see how it goes. For now, we will see how we can run this particular distributed data parallel methodology on a Google virtual machine with a GPU. So for reference of the code that I am trying to run, if you go to the Pytorch Ignite, there are tutorials, and this is the particular reference I am using. They have code that you can run. They are using CIFAR data. Basically, CIFAR is a set of images that are divided into around 10 different categories, and there are around 50,000 odd images, I guess. It could be here and there, but you can check it out. So they use the cipher images. For reference also, you can go to this site and you can look it up. So Ignite is a high level API you can use with plain PyTorch also, but Ignite makes it a little easier. As you can see, the dependencies are Pytorch, Ignite, install, under and fire, and then you can download that. You need to download the data from torchvision.datasets. So I just want to do a POC here and see how it goes on Google virtual machine and how the distributed training can be run. So quickly, guys, let us go into our Google VM. So I already spun up an instance. Basically, I'll show you how I have done it. Let me go to marketplace. And I'm using a deep learning VM. There are other things like Google AI platform. And then there is a newer one called Vortex, AI Vortex, but those require you to spend more money on them, and they are still in, I mean, the Google Vortex is newer version. So once that comes up, we can quickly learn on that how to do it. For now, let's just search for a deep learning VM and see how we can implement it on this. So just for your information, you can enable GPUs only on a non-free tier one. So you need to activate the paid one. So I just activated my paid one, and let's click launch. So as you can see, there are different zones, and I see that the GPUs are not available in all the zones. I'm using NVIDIA T4 version of GPU. So for example, I use the Asia East 1A. That is where I could find a GPU for myself. And here you could see that it has a CPU that is associated with the GPU. I'm using a single GPU because that was what was available for me. See, if I take more than one, I am getting this type of error. Basically, I need to request for upgrading my quota. So for now, I'll just go with one, and I will be using the Pytorch 1.12 CUDA 11.3 framework or image on my GPU platform. I'm also saying that asking Google to install NVIDIA GPU drivers that will help me run the multi-processing GPU related processes on my machine. And I also want access to Jupyter Lab, and I would say I accept terms and GCP marketplace terms. And let me go ahead and click deploy. This will take a while, friends. So in the meantime, what I would do is we'll just walk through the code. I just put that particular tutorial code in my PyCharm, and I have a README file where I have updated the instructions. These instructions are very helpful. So that's what I have committed in this um, Git repo, and it is public, so you can get access to this in the readme file, but the actual tutorial reference is here. They don't mention about the how the nitty-gritties of deploying it on Google virtual machine. So I have, so this, the idea of this particular this specific tutorial is to just make it easier for you to take this particular code from which was provided by these people and integrate it and deploy it and on a Google virtual machine. So I just copied the code here. We'll just walk through the code. They have imported the necessary libraries, the Torch APIs and the Ignite APIs. As I mentioned earlier, Ignite is a high-level API that supports distributed training on Pytorch libraries. They have a standard count config, the seed, the path where the images are stored. This is the path where we will um, put the all these IFR image files. Already um, downloaded the image files in my local, but I would be transferring them onto the Google VM. The model we would be using is ResNet, and this is the batch size, the decay, number of workers, or the number of processes, the epochs or the number of iterations, the learning rate. Um, the backend is actually the CPU or GPU that you would be using. Very soon you will see what kind of backend we'll be using. We'll be using GPU, and the processes per node. We are not using ClearML or AMP. AMP is like an amplified or not amplified, but it's a fast. It implements a faster training process on a uh, like this GPU platforms or TPU platforms. So we are not using that as of now. So this is the there are a lot of helper methods that transform the image, they crop it, and they are 32 by 32 images, pixel images, and they do a random horizontal flip for all the images and then normalize it. So that's to this particular method, and then this particular thing gets the data from the path and sets the batch size, number of workers, shuffles it so that all the images there is no overfitting or anything. Uh, and then this one gets the ResNet model. This optimizes using a stochastic gradient descent optimizer. It uses the learning rate. Basically, gradient descent function is a methodology where you use the
tangent of the feature map, tangent of the feature map, uh, which is called the gradient, and it is used to minimize the loss function. So that's why it is called stochastic gradient descent. And we want to, the idea is to minimize the loss. At what point are the uh, slope at which there is minimum loss, the point at which there is a minimum loss. So that's to the optimizer, and we use cross entropy loss, and the scheduler, and there are checkpoints, and this is the training method, transforms the output. It uses the model, the optimizer, and the criteria, the device, and resume from is from the checkpoint. We are not using any checkpoint at this point. And this is related to the parallel processing, the rank 0 logging thing. This is where the training starts. We get the data, we create the trainer, and we have the accuracy and the loss function for the metrics, and we are running on a GPU instance. If you want to run on a TPU, this is what you would use. We would use the backend as XLA TPU. If you are running on a Jupyter notebook, there are again minor changes here. We want to fork it on the same Jupyter notebook. And this particular thing will, section of run code, will run it on a GPU machine, and we invoke it using the fire endpoint. That's to the code, and let's go back and see whether the image has been created. Yeah, it has been deployed. It has warnings, that's the deprecation warnings. That's okay. Let's go and see what is this VM. So I'll just, for reference, I will copy this here because I have another VM instance. So for now, I'll just copy it here, the second one. And because they are in two different regions, and this is the VM name, this is my project name. So and this is the path where I have my data. So the VM is created. I had created a VM earlier, so I just want to run that. So I just want to SSH into this particular VM. So let me see.
So this is the Google Cloud command I would use to SSH into this VM. As you can see, it's a new VM. So now what I would do is I would SCP my Python script, which is this, and the cipher data into this particular VM. I would do it from my Mac. Okay, these are my deployments. Let me go back to my compute engines VM instances and check them out. So here they are there. I'm gonna select this and stay start. Let's see. So this has been assigned a ephemeral external IP. So first we'll run it on one machine, and if we get lucky, then we'll try to run it on two different nodes. So let's see how that goes. So for that, I'm going to refer this commands that they have given. We have two nodes. Processes per node is 1. Have another place where they have given clearly. Yeah, so maybe we can follow this. The node is just put 1, and then just put it in a single line. It's for convenience sake. And we will make one of the nodes master for now. I mean, let's go and see how that comes. The VM is coming up. Let's see, let's make this guy master. Master port 2222. Then we'll the worker node, we'll use the other one. And the script file we are using is distrain.py. So we'll replace that in both the invocations. The backend is NCCL and the master port in both of them is this thing, master IP address 0, number of nodes is 1. We'll just save this file and let me commit this into the main. So let's go back and see if our Google VM has been created. Let me refresh it. It's still starting up, or maybe he didn't allocate me my GPU because I already used up a GPU maybe. So he has not yet assigned me my external IP. So I think we are already logged in into this guy and we transferred the data. So the data is here, whatever data, the script, you can see the script here and the readme file and the C4 images are here. Okay, we'll see what is there in C4 images. Yeah, we have the tar file and the C4 folder. Okay. So we are here. We'll just run our we have to install Fire and Pytorch Ignite, otherwise it won't run. I can show you what happens. Sorry. If I run the script right now. So as you saw earlier, when we were creating the VM, it was a Pytorch image that was already installed with AMD drivers that would support the GPU run. So this is already equipped with all the drivers, AMD drivers that will help enable a GPU run associated with that particular CPU. So it is complaining that Fire is not installed. So Python is already installed on this VM. So we just install Fire, and then again we'll run and see what happens. So this time it says Ignite is not there. Ignite is again the high level API that is used to run the parallel training. So we'll install Pytorch Ignite also. Then we'll try again. So there is another warning which says missing XLA configuration. Basically it is looking for a TPU in the machine. This is I think it's a bug with Google where it is looking for a TPU or bug or some kind of thing that they needs to set it right. It's looking for a TPU. Basically the image is set up for GPU, but it is looking for a TPU. It should not be the case. So I fixed it. I googled some stuff and I had to install the Google TPU client. We are not running on a Google TPU. It's the machine itself has only GPU, but it is looking for TPU. So that is a ambiguity with Google platform as of now. So I'm installing the Cloud TPU client. And then I have to run this script again, the training script. Okay, now let's run the training script and see what happens. So it did go forward in execution, but what we see is it's saying the no tensor board. So this is another dependency that we have to install for our program to run successfully. So it installed tensor board. Now let's run our script and see if it is able to do the training on a single GPU. So it loaded the config, and basically we are saying that one node, one process per node, and there is only one node and one GPU. Backend is GPU, and this is supposed to train on this main thing. And the idea is because the script can be changed very easily for with very less changes for multiple GPUs or multiple nodes. So the idea is if we run it on one GPU, we are very well equipped to run it on multiple GPUs, provided the network access is taken care of. So that is the idea. And if I do want to run it on multiple nodes, but there is a cost constraint, and also because Google is uh, going into a newer platform with Vortex, AI Vortex, that is something very interesting that we need to look at what happens there. So right now it's just a plain deep learning VM we are looking at. So as you can see, the training is successfully happening. There are 5 epochs that we have configured. It says the number of processes is 2. For one for training and one for test. And it is calculating the accuracy and loss for each epoch. and it has run the fourth epoch as well. And it's telling overall accuracy is 66 and loss is 0.95. It's not good, but reasonable in the sense that we have run only 5 epochs, very short time. And I think because it's a GPU, it is running it very fast. If you are running it on our local machine or on Kaggle, sorry, on Collab, it would be not that fast because it's a dedicated machine, it's faster. So now we clearly see that this particular machine is running fast and it's able to train. And let's go back and see if our deep learning machine has a so maybe let us this is not starting up probably because I have a GPU constraint. I will try again some other time and see after my quota increases if I am able to run multiple nodes. I can run with one GPU each. That brings an end to today's session, my friends. So see you next time with some other interesting tutorial.